The traveling salesman problem. So this is this sort of traveling salesman is a made-up scenario, but we're going to see that this type of made-up scenario actually arises many, many times in the real world. It's extremely important to the way that a lot of our basic technologies work. By basic, I mean like modern, things like the internet. It's not a basic type of technology, but I mean things which are very important to our life that we use all the time without even thinking about it. Many of them rely on solutions to what we call the traveling salesman problem. I'm going to write TSP for traveling salesman problem. It involves this is sort of a word problem about the classical case is the traveling salesman is like some guy selling globes or something who goes to people's houses, has to visit a bunch of people's houses. The guy wakes up in the morning, he has a list from his boss, you got to go to these 15 houses. It's up to the guy to decide what order he visits them in, and the question is the question that the traveling salesman wants to have answered for himself is, what's the best route to go so that I can visit all 15 of these places the fastest, right? That's what the traveling salesman problem is about. I have a slightly different version of that. This is more simple and more kind of. Here's a picture of the United States. This is my bogus drawing. That's Florida, right? That's we live somewhere around here, okay? And let's say that I am trying to visit all my friends who live all over the United States. Now, some of them live in the Boston area because that's where I'm from. Some of them live around New Jersey. That's where my wife is from, New Jersey and Philadelphia. So she has friends in those areas. And because she's my wife, those people are now my friends, because that's how marriage works. So I'm going to say, I'm putting the airport codes. Let's say this is EWR, that's the Newark airport in New Jersey. And then there's also, here is Philadelphia. And then here is, I also have friends in Los Angeles, because I went to UCLA for grad school. So let's imagine, actually, to be honest, after we finished grad school, me and all my friends left LA, so I actually don't know anyone who still lives there. But let's imagine that I did. Anyway, let's say I want to visit all 4 of these cities, starting and ending in Newark. So I want to go. I'll visit LAX, Boston, and Philadelphia. And I start and end in Newark, all right? The question is, how can I do this? I'm going to use airplanes to do this. How can I do this for the cheapest? And I will tell you what each possible flight is going to cost me. So we don't even care about this picture anymore. I'm going to tell you what all possible flights that I could take from one of those to another. I made a little chart here, and these are made-up numbers. These numbers are actually way too small to be realistic, but don't matter. So I made a chart. I'm going to write it this way. Newark, Philadelphia, Boston. Okay, Newark to LAX is, I'm just going to write all these down, 400. All right, let's say these are the prices for each of these flights, Newark, Philadelphia, Boston, and LAX. And these are the prices. So when you see Newark to LAX is 400, LAX to Newark is also the same. I know this is not quite how it works in the real world, but let's just assume, for the sake of simplicity, that it costs you the same to go Newark to LAX as it does LAX back to Newark. Okay, the question is just, what's the cheapest route that I can take? Starting at Newark, and I have to visit LAX, Boston, and Philadelphia. The cheapest total cost that I want to do here. What's the cheapest total cost? And what, itinerary will get me that cheapest possible cost. All right. What does this have to do with graph theory? It turns out this actually does have quite a lot to do with graph theory, and also, in particular, graph theory of a complete graph. Let's look at this. I'm going to draw over here. We are going to represent this problem, which I wrote as this little chart here. More commonly, it will be given to you like a graph. And this is a complete graph with 4 vertices. Each vertex represents one of these places. So I'm going to call them L, B, P, and E, just to match the first letter of each of these. So this is LAX, Boston, Philadelphia, and Newark. This is a complete graph. These edges represent each of those flights, right? Each of these flights is represented by one of these edges. So this diagonal edge, for instance, is the flight from LAX to Philadelphia. And I'm going to just stick these numbers right on the edges. So from L to B, that's the flight from LAX to Boston, which has price $250. So I'm going to put $250 right there. From B to P, Boston to Philadelphia, the price is $100. All right. L to P, LAX to Philadelphia is $200. I'll try and do this in an unambiguous way. $200 right there. L to E is $400. E to B is $200 also. And then this one, E to P, is $100. All right. Now that you have the graph, you don't need this chart anymore. All of that information has been encoded on this graph. This is a graph with some extra information. It has these extra numbers on it. This is called a weighted graph. Weighted refers to those numbers. So each edge has a weight. A weight. The weights here represent the prices. All right. In other examples, they could represent other things. For the traveling salesman, the guy going to the different houses, maybe the weights would represent like distances between the different houses or whatever. Anyway, this is called a weighted graph. And the question that I asked before, what's the cheapest possible total route here, starting and ending at Newark? We can translate that into a question about this graph. The question is, what does it look like to visit every city here, starting and ending at Newark? If I want to just hit every city once, it doesn't mean you have to do all of these flights. In fact, you only have to do 4 of them. That's a Hamilton circuit, right? It has to hit all of these 4 vertices. I don't care about hitting edges. That's a Hamilton circuit. So the question then becomes, what is the Hamilton circuit with cheapest total weight? All right, and this right here is what mathematicians call the traveling salesman problem, or the TSP. If you are talking to, if you meet a mathematician in the club, and they're like, "Hey, you know about the traveling salesman problem?" This is what they're talking about. They're talking about the problem where if you have a graph with weights on it, can you find the lowest total cost Hamilton circuit? That's what the traveling salesman problem is. I'm here to tell you it's super important in the real world today, and we'll talk more about that next time. But for now, let's try and answer specifically that question about this graph. There are a few techniques for solving the traveling salesman problem that we're going to talk about, but at this point, I don't want to get too fancy about this. I want to just describe the sort of simplest way to solve the traveling salesman problem. By simple, I mean most kind of boneheaded. You don't have to have any big ideas. This is not high concept. If you have no idea about anything, you could simply check all possible Hamilton circuits. So I'm going to write down all possible Hamilton circuits. There's not that many in this case. In this problem, I want ones which begin and end at the E. And this would consist of E, E, right? There are 3 other letters, L, B, P. And these 3 just have to be put in some order. So maybe I'll just start like in alphabetical order as my first choice. E, B, L, P, E. That's one possible Hamilton circuit. What are the other ones? We can write them down. They're just all possible rearrangements of these 3 letters. So there's another one which begins with B. That would be EBPLE, right? There's ones, how about the ones which begin with L? Begin, I mean in the second position. All of these will start with E's. LBPE is one. There's also LPBE. And then finally there are two which have a P in that position. So PBLE, PLBE. All right, these are all the possible Hamilton circuits in this graph. And now we can simply figure out the cost for all of them and just write it down. So for example, this one, what is the cost of that? I have to look at each of the four legs here. E to B, first of all, is 200. Next is B to L is 250. Next is L to P is 200. Next is P to E is 100. And when we add those all up, sorry, I'm off the side of my getting to the end. When you add that up, you can do this without too much trouble. That's 400, 650, 750. All right, so this route here costs 750 total. And you can just do the same thing for all of the other ones. All right, how about you guys try that? Can I let you all try? For each one of these, find the four edges. You should be adding together four things every time. Don't forget to include the ones on the front and on the end with the E. See if you can add them up and then figure out which one is the least. I'll give you a few moments. All right, did you do them? I did them. I hope that you got 900 for this one, EBPLE, and 850 for this one. You had to add those numbers together. It'll take you a few moments, but nothing weird happens. I got three more that I didn't write down, but here's a little pro tip. Check it out. This one, ELBPE. Every one of these, I have already written its own reverse, ELBPE. I already wrote this one read backwards, which is EBPLE. It's that one. And because these edges are symmetrical, when you go one way, it's the same weight as going the other way. This one will have the same weight. It's going to be 900. All right? I hope that that's what you got when you did that one. This one, EPBLE, has the same weight as ELBPE, and I did that already, is 850. And then this last one, EPLBE, should be the same as EBLPE, which is that one, which was 750. And so my answer is the 750 is the cheapest. So the best route to do would be EPLBE or EBLPE. Exclamation. All right? Aren't you excited that we figured that out? Okay, this is the traveling salesman problem. And that's how you solve it. This, like I said, we're going to talk about several ways to solve the traveling salesman. This one is the least high concept. You don't really have to have any ideas. You just write down all possible Hamilton circuits and figure out the weight for each one. All right. This procedure that we just did to find the minimum cost Hamilton circuit, that procedure has a name. It's called the brute force algorithm. The way you do the brute force algorithm, you simply write down all possible Hamilton circuits. Write down all Hamilton circuits. And I will say, parenthetically, there are, like we said, n minus 1 factorial of them, which is a big number if n is large. Write down all Hamilton circuits, and then we just compute the cost for each. And choose the smallest, all right? The brute force algorithm. This is called brute force because you're not actually thinking or really trying to analyze the problem with any kind of sophisticated idea. All you're doing is simply writing down all possibilities and checking them all. And this is a common strategy actually in many types of mathematical problems, and it's typically called brute force. is basically just a fancy way of doing guess and check, where you're doing all possible guesses and then checking them all. This is something that, in a typical real world example, you don't want to do this by hand. You would use a computer if you really wanted to do this in a practical way. I'm going to say, though, for the traveling salesman problem, brute force for traveling salesman problem is not practical, because there are so many alternatives you have to check. You know, the example we just did had only 4 points in it. If you had more than that, it's going to be far more. Brute force for a traveling salesman problem is not practical, even for a computer. This is an issue with the brute force. When people are trying to do this in the real world, even using a computer, this is not a great strategy. Although it will, in theory, give you the correct answer every time, it is not practical to do. I just want to explain a bit about who wants to do this in the real world, what does it matter, and why is this not practical even for computers to do. The traveling salesman problem does arise in the real world in many scenarios. The typical scenario would be traveling salesman problem arises in the real world in any, I would say, something like a multi-stop route planning problem. I'm thinking of something like package delivery guys or girls or whatever. Package delivery. How about a package delivery truck? Say the guy who works for UPS, like the ordinary mailman. I believe they more or less go the same route every day, and they plan out those routes. They have to visit every house every day. But it's a little more interesting with, say, a package delivery truck, where they get up in the morning, they have a truck full of packages at different addresses, and they just have to go to those different addresses. Maybe there's 50 different addresses in their truck. I don't know how big those trucks are. Let's just say the truck guy, every morning they get 30 new addresses to visit. And somebody has to figure out where you're going to go first. You go to this one, then this one, then this one. You need to figure out what route to take them in, which will give you be able to do it the fastest is probably what they care about. Although they might also care about something like using the least amount of fuel or whatever. They have some things that they need to care about. But anyway, they are looking for the minimal cost in some sense, where cost might mean dollars, it might mean distance, whatever. And about 30 maybe they have every day, and this they need to do every day is different, right, for the guy on the truck. I'm here to tell you, I don't think they leave it up to the guy driving the truck to make this decision. Probably when the person driving the truck gets up in the morning, they get a big list of where they need to go, and they also are told which order to do them in. Somebody had to figure out, how do you figure out a route for that? This is maybe a little bit of a smaller scale. A larger scale version of a problem like this would be, just think about like all the trucks in the United States that have to bring stuff from one place to another. All of those trucks, there needs to be some kind of large scale planning for where they all go, which is a similar situation, only it's not 30 then, it's like, many thousands of spots that you have to hit on your routes. Now, if you're talking about all trucks at once, that's not really a single Hamilton circuit. It's some kind of collection of many different Hamilton circuits, but it's a similar problem. The traveling salesman problem was also a big deal. This is not such a big deal anymore because the technology has changed a little bit, but it was also a big deal in computer data access. Nowadays, we've changed the way that we store data, but it used to be the most common way to store data was on computer hard drives, which were kind of like CDs or DVDs, but you would never see the disc. But it had a spinning disc inside and a little sort of arm which can read the data. It looked kind of like an old record player, although much smaller. And the arm doesn't actually touch the disk. It has a magnetic thing that can read the magnetic information on the disk without touching it. And the information would be written just like on a CD or on a record or something in different places on the disk in a circle. So the disk spins and the little head would move back and forth, and it would be able to read the distant, or it would be able to read the data as the data spins by underneath it. When data is stored on a computer, it is not typically stored all together. That's because your disk, as you put stuff on the disk, and then after a while stuff gets erased, gets replaced. Over time, your computer is using different parts of the disk for different things. And after a while, certain things might be so big, if you want to download a big file or something, it might be too large to put in any one continuous piece of the disk. This happens all the time. And so your computer will fragment the data and store it in different spots physically on the disk. You don't actually care about this at all as the user of the computer. None of this matters to you, but it is true deep down inside the computer. If you're listening to a song that you downloaded, that downloaded song occupies a certain amount of space on the disk, and it's probably not all in one continuous piece. It's probably got jumps in the middle where your computer has to jump from one place on the disk to another. Anyway, that's really the question. If you want to load a large file, let's say that file is in 4 pieces on the disk. Let's say piece A, piece B, piece C, piece D. While the computer is running, when it is instructed to load this whole file, it has to go to these 4 places on the disk. This little arm and the spinny thing has to actually travel to these 4 places on the disk. And the computer needs to figure out what is the fastest way that I'm supposed to go to those 4 places. Now, this is only going to take a fraction of a second anyway, so you might feel like, well, what does it really matter if it takes the fastest route or not? Those fractions of a second, everything in the computer is only taking fractions of a second. So fractions of a second are actually meaningful durations of time when you're talking about the operations of the computer. The computer wants to do this as fast as possible because everything else in the computer is happening so fast. You don't want this to be the slowest thing going on in your computer, right? You need this to be able to keep up with everything else that's happening really fast. Anyway, data access. Data typically is stored in a fragmented way, and when you want to read it, you have to go to various spots and pick it up. You got to go here, pick that up, go here. Now, what order are you going to do them in? That's a traveling salesman problem. You have to figure out what's the best route between these 4 locations on the disk. All right, computer, data, access, and many other things. Can I just say, etc. There are many situations in which people need to decide efficient routes between multiple points. This happens all the time, and it involves solving the traveling salesman problem. So finding solutions to the traveling salesman problem is super important in the real world. Let's talk about the brute force strategy and why I said the brute force actually in the real world is not practical even for computers. Check it out. Trying to solve the traveling salesman problem by brute force for n points requires n minus 1 factorial steps, right? You have to write down all the Hamilton circuits. That's how many there are. And then for each of those, you add together all the numbers. And like I said before, this is going to be a very large number if n is pretty big. Specifically, I ran the numbers on this. Check it out. Let's imagine that I'm using a computer. So let's say we have computers have different speeds. Some computers are faster than others. Let's say our computer is using what they call 4 gigahertz processor. This gigahertz means operations per second, and giga means billion. That hertz means operations per second. Giga means billion. So this means that my computer can do, let's say we have a 4 gigahertz processor. That means we can do 4 billion steps per second. And this is a realistic, typical. I don't know. This is like a decent computer can do 4 gigahertz, 4 billion steps per second. Where so technically step means like usually means like a single addition of numbers. Although we are going. Let's just assume that each of these steps in the traveling salesman problem can be done in one single clock cycle of the computer, and that happens 4 billion times per second. This is being a little generous. Actual computer wouldn't be able to do this in just a single step each time, but whatever. Let's say we have a 4 gigahertz processor. Let's just do some simple arithmetic here. How long would it take to solve traveling salesman problem for, let's say, n equals 4? This is the one like we did with the 4, LAX, Boston, whatever. To solve this traveling salesman problem for n equals 4, we have 3 factorial steps, and we have 4 billion steps per second. And so, how much time will it take? Well, it would be 3 factorial, which is 6, divided by 4 billion. And I did this on my calculator. I got this many seconds. 0.0000000015 seconds. So that's how long the computer will take to solve that problem that we just did by hand. This is very fast, right? What if it was more than n equals 4? What about n equals 5? I'm just going to try and run through the same numbers. This is simple. You could do this on your calculator if you wanted to. And the numbers really, the specific numbers aren't that important. I'm just trying to give you a feel for what these things would look like. What about n equals 5? Okay, then we have 4 factorial steps. And again, we're dividing by 4 billion. This one, when I put this in my calculator, I got 4 factorial is 24. Divide by 4 billion. I got 0.000006.0000. So, and this, seconds. That's how long it would take for n equals 5 traveling salesman problem. No problem, right? This is still very fast. As you increase this number, it will cause this, like when I go to n equals 6, it would now look like 5 factorial over 4 billion. Whatever. This is also a very small number. These numbers don't stay very small forever, though. Check it out. If you go to n equals 13, what happens? You get 12 factorial divided by 4 billion. And 12 factorial is a very big number, right? This is 12 times 11 times 10 times 9 times 8, etc., all the way down to 1. I plugged this into my calculator. Here's what I got. 0.12 seconds. Now, this is still not very long in ordinary human terms, but it's getting there, right? It's certainly much longer than that, right? 12.12 seconds. Still doable. What if I just let's say go to n equals 16? Remember, the traveling salesman problem, say for the guy in the package truck, he wants to be able to solve this problem on the order of like n equals 30, because that's how many deliveries he's got to do. So we're not there yet. What about n equals 16? In this case, we're going to get 15 factorial divided by 4 billion. And this I plugged into my calculator. This was 326 seconds. This is actually kind of a long time. So if you divide by 5, or divide by 60, this is about 5 minutes, right? Now, 5 minutes is not so long out of your day, but have you ever actually waited for 5 minutes for your computer to do something? Maybe you have, but that's a long time when you're using your computer. To wait for your computer to do something for 5 minutes is kind of a long time. Pretty long, although still not such a big deal. Remember, the package guy wants to do this procedure every morning when he wakes up. He's got his 30 packages. He wants to type that into the computer, and it'll tell him which route to use. If it only takes 5 minutes, not a big deal, right? He can, have an extra cup of coffee. But what if these numbers, they get big pretty fast? How about n equals 20? Now we're talking about 19 factorial over 4 billion. This, when I plugged into my calculator, I got, you ready for this? 351 days. All right? This is absolutely unacceptable. This means if the guy has 20 packages in his truck, to actually find the best route using brute force will take almost a year on a normal computer. That is straight up not not realistic, right? In theory, you could do this if you wanted to, but this is a computation you want to do every day. This absolutely is unacceptable. What if we go, remember I said at the beginning, really, I'm thinking the truck has maybe 30 packages. If we go all the way to 30 and do this number, we get 29 factorial divided by 4 billion. This, when you plug it in, is 7 times 10 to the 13 years. That means a 7 with 13 zeros after it. 1, 2, 3, 4. Yeah, I'm going to write them. 5, 6, 7, 8, 9, 10, 11, 12, 13. This many years. 70 trillion years to solve a single traveling salesman problem with n equals 30. I will have you know, just for comparison, the universe, since, from the present day, since the Big Bang, is estimated about 15 billion years. This is 70 trillion years. Far longer than the lifespan of the universe. And this is what the package guy wants to do every day. This is a serious problem. So the brute force, I'm just giving you all these big numbers just to convince you of this fact. Brute force method to solve traveling salesman problem is not workable in the real world. Brute force is not practical in the real world. Even if you're using a computer. Now, you might say, well, probably the package guy, of course, the package guy driving the truck is not the one who's going to try to make these computations. Probably UPS or whoever has some massive supercomputer somewhere that can do this computation for you. The answer is no, they don't. A single computer would take 70 trillion years to do this computation. What are you going to do? Get every computer in the world, every computer on Earth, put them all together? It would still take you, at least 100 billion years to do the computation. So it's not going to work, even if you use some kind of imaginary supercomputer. Computations of that order are simply not possible at all. Even if the entire Earth were transformed into some mega planet-sized computer, maybe be able to do 30, but give it n equals 50 and it would not be able to do it. So the brute force is not practical in the real world. We need better methods. I'm here to tell you this is a strange but true fact. No better method is known. As of today, as of me recording this video, there is no better method that is known to solve the traveling salesman problem, which always gives the best solution. There are some very simple improvements which only improve a little bit. Like I said when we did that first example, you can realize that half of the circuits that you write down are actually duplicates of another half. So really, you don't have to check all of them. You only have to check half of them. But that really is not, in terms of these practical considerations, that's not much of an improvement. You go from 70 trillion to 35 trillion if you only count half of them. Not a big deal, right? That is still an unacceptable number of steps that you have to do. No better method, no significantly better. Like I said, there are some cheap tricks you can do to get some amount of improvement, but no significant improvement which would allow this problem to be solved in a practical way in the real world. No better method is known. If you think you have an idea, let me know. You will become world famous if you can find a better method to solve the traveling salesman problem than the brute force. All right? No better method is known which always gives the best solutions. So, how do they actually do this in the real world? How does the UPS truck figure out where to drive its 30 packages? Obviously they do something. The answer is they are not doing the best route possible because it is computationally impossible for them to figure that out. So, this is an example of a math problem which is simply too hard to do in the real world, even though it's important for people to do in the real world. No better method is known which always gives the best solution. So, in the real world, we use what are called approximate algorithms. Remember, algorithm just means some kind of procedure which will give you the answer. there is no practical procedure you can use which will always give you the correct answer. So instead, we use what they call approximate algorithms. That is some kind of procedure which gives you an answer which is pretty good, although maybe not necessarily the absolute best. So we use approximate algorithms. These give decent answers, maybe not the best. And this is what's being used every day by the guys in the package trucks and all these other kinds of routing problems that you don't even think about from in your own life. Those folks driving the trucks are not about. They are not doing the best possible routes every time. They're not. They are doing pretty good routes, which are derived using these faster algorithms, which you can actually do in just a few moments, which will give you pretty good results, although not necessarily the best ones every time. So what we're going to do for the remainder of our time together, we're going to talk about 2 approximate algorithms for finding pretty good solutions to the traveling salesman problem. If you want the true best solution, you must use brute force, which is impractical in the real world. If you just want pretty good solutions, there are other methods that you can use which are practical to do. We're going to talk about 2 of them. First one I want to talk about is called the sorted edges procedure, and it's very easy to do. Actually, both of them are very easy to do. So let's talk about the sorted edges procedure. I'm just going to say, I already said this, but this produces a pretty good solution to the traveling salesman problem. Not necessarily the best. And if you're doing this for a traveling salesman problem with a large n, say n equals 30, it's almost guaranteed not to give you the best. Finding the true best solution is like a needle in a haystack, which even computers are not capable of doing. But the sorted edges procedure will give you a pretty good solution to the traveling salesman problem. And here's how you do it. Let's just do a quick example. Let's do that LAX business. We have the 4 cities and the numbers. I will draw the numbers again. And this is 250. This was a 200. This was another 200. R to P was a 100. E to P was also a 100. And then this was a 450. All right, in the sorted edges procedure, it's called the sorted edges because you write down, first of all, just what are all the weights in order. That's the sorted. The weights are 100, 100, 200, 200, 250, and 450. So I write them down. 100, 100, 200, 200, 250, and 450. Okay, these are the edges. And now what we do is we try to build a Hamilton circuit by choosing the edges in this order. So try to build a Hamilton circuit by choosing these edges in this order. So what I mean is, first we're going to try to use the 100, then the other 100, then we're going to try to use the 200, then the other 200. This is because we want to minimize the total cost, so we're going to try to use these. You would never say, oh, I really want to do this 400 first. No, you should try to do the 100s. You should only do the 400 if it's absolutely necessary. So what we're going to do is try to build a Hamilton circuit by choosing these edges in this order, and just like we talked about before, there are certain things which you're not allowed to do when you are building your circuit, and I will refresh your memory. We pick edges, pick edges from cheapest to most expensive. And there are 2 rules you got to abide by as you are picking those edges. The first rule is never make 3 edges meet at a vertex. Because, like we talked about last time, when you are making a Hamilton circuit, the Hamilton circuit meets every vertex 2 times, all right? So while you are choosing the edges one after another, you can never choose edges which make 3 of them meet at the same vertex. That's not allowed in a Hamilton circuit. So never make 3 edges meet at a vertex, and also never make a smaller circuit. This is like the 2 things that we talked about last time about finding Hamilton circuits. Never make a smaller circuit. All right. How we do it. First, I choose 100. Now, there are 2 labeled 100. The sorted edges procedure is slightly ambiguous if you have copies among the labels. Usually, most examples we do, every label or every weight will be different. There won't be any ties. We have 200s here. But anyway, I'm going to try to use 100 and then try to use the other 100. And it turns out these 200s, we can use them both. So I'm just going to pick edges by sort of scribbling them in. I'm going to scribble one at a time. And eventually I will build a Hamilton circuit. So I use that 100, I use that 100. Next, we try to use a 200. Now there are 2 200s. Can we use one of them? Actually, let's look at this diagonal first. That 200 is not allowed because it makes the smaller circuit right here. All right. So we do not use this 200 because this one makes a smaller circuit. That was this one. So this one is not allowed for us to pick. What about the other 200? That other 200 is also not allowed because it meets this one. It makes this vertex have 3 edges at it. So this 200 is also not allowed. This is because it makes 3 at P, right? P here, if you chose that edge, P would have 3 vertices on it, which is also not allowed. Okay, then we got to take the 250 next, which is allowed. It doesn't make a smaller circuit, and it also doesn't make 3 edges meet. And then we got to take the 450, which is allowed. And we have our Hamilton circuit now. So the circuit that we get in this case, the sorted edges, gives the circuit. And if you want to write your answer, starting at E, because that's how we were doing this before. There's actually 2 ways around you could read this, but let's go this way. ELBPE. And the total cost of this, you can add up if you want. 450 plus 250 plus 100 plus 100. That's 900, right? So this is an example where the sorted edges procedure actually doesn't get you a very good answer. The idea behind the sorted edges is it's supposed to usually give you a good answer. There's no guarantee that it's going to give you the best answer. That's what you get for using approximate algorithms. They don't always give you the best answer. Sometimes they give you a bad answer. The sorted edges, for large examples, gives you a pretty good answer. Let's try some bigger examples. All right, I got a big one here on 6 points. All right, this edge has 4. This edge, A to B, has 8. Let's draw all the A edges first. A to E, that edge has a 13. A to D, this edge. Actually, I'm going to draw all the edges first and then put my labels. All right, those are all the edges. Let's label them. So A to F is 4. A to E is 13. A to D is 12. A to C is 10, and then A to B is 8. All right, how about the edges from B? B to F is 5. B to E is 19. B to D is 6. B to C is 7. Okay, the other edges from C. C to F is 10. C to E is 15. C to D is 2. D to E is 13. D to F is 17. E to F is 1. And I think I got all the edges labeled. All right, your job is to find a... How about, if this were a homework problem, I would say something like, find a good Hamilton circuit. How about, I'll tell you, just start and end, starting and ending at C, how about? All right? Now, we didn't actually talk about how to do this. This business starting and ending at C, you should ignore that completely at the beginning of the problem. You are going to find the Hamilton circuit by scribbling edges, and then just when you say your answer, you say it in terms of a circuit which starts and ends at C. How are we going to scribble edges is according to the ordering of the edges when I sort them. So you're supposed to write down all of the weights in order from lowest to greatest. There's kind of a lot of them here, but I'm going to try and write them down here. The lowest is a 1. Is there a 2? Yes, there's a 2. I think there's no 3 here. The next would be a 4. Then there's a 5. Then there's a 6, a 7, a 8. I don't see a 9. There's a 10. There's another 10. So there's 2 10s. Hopefully that won't be a problem for us. No 11. There's a 12. There's a 13. There's another 13. There's I don't see a 14. I see a 15. And 16, 17. And a 19. All right. I think I wrote them all down. You will see that sometimes the hardest part of doing the sorted edges procedure is making sure you actually got them all and didn't miss any. But anyway, I think that's all of them. Let's scribble them in then. We're going to begin with the 1. I take the 1. All right. I take the 1. The 2. Can I use the 2? Where's the 2? Here. Yes, I can use the 2. Remember, every time you're just checking, does it make 3 meet at an edge? If so, you can't do it. Or does it make a smaller circuit? If so, you can't do it. This 2 here, it's going to be fine. All right, what about the 4? Can I use the 4? I can use the 4. It does not make 3 meet at an edge, and it also does not make a smaller circuit, so the 4 is fine. What about the 5? The 5 goes here. Actually, I cannot use the 5 now because it's going to make 3 edges meet at the F. So the 5 is excluded. What about the 6? The 6 can go here, and that will be fine. It doesn't make a circuit, and it also doesn't make 3 edges meeting at a single vertex. So the 6 is fine. The 7. What about the 7? The 7 is here. That makes a smaller circuit, right? So the 7 is not allowed. The 8. The 8 goes across the top. That's fine. It doesn't make a circuit, and it also doesn't connect 3 edges at the same vertex. All right. That one I used. Okay, actually, I've picked 5 edges so far. We're only looking for 6 edges total. There's only one more that we could pick to complete the circuit. It would be from E to C. If you like, you could think through all these other ones. Every single one of them will be excluded for some reason or another. Like a 10, this 10 here will make 3 meet at A, so that's not allowed. This 10, where's the other 10? Here will make 3 meet at F, so that's not allowed. The 12 here will make 3 meet at A, so that's not allowed. This 13 will make 3 meet at D. The other 13 will make 3, no, it makes 3 at A. It also makes a smaller circuit. The 15 is legal right there. All right. And that's it. I've made my Hamilton circuit, right? It hits every one of these vertices one time. This is how we do the sorted edges procedure. What about this? I said find a Hamilton circuit starting and ending at C. Well, I found the Hamilton circuit. When you write down your answer, you simply write it as if it were starting at C. This starting at C business doesn't affect how you find it at all. It just affects how you write your final answer. So I'm going to write it here. Now you could go to D first or you could go to E first. Those are 2 different, both correct answers. Let's just go to D first. So my answer is C, D, B, then to A, then F, then E, and back to C. All right, this is how we do the sorted edges procedure. I got one for you to try. All right, this one has 5 points. A, B, C, D, E. Can I just comment? The sorted edges is much, much faster than the brute force enumeration because all you have to do is be able to choose the cheapest edge each time. Sort the edges out, write all the edges down in order. Even if you had 30 packages in the truck, there's only like, there's not that many edges. Something like under 1,000, I believe, if you write down a complete graph with 30 vertices and draw all the edges. You wouldn't want to do that by hand, but your computer can definitely do it very quickly. All right, anyway, here are the edges, and I got to write the weights down. So from A to E, the weight is 15. From A to D, the weight is 27. From A to C, the weight is 20. From A to B, the weight is 21. All right, from B to E, the weight is 12. From B to D, the weight is 19. From B to C, the weight is 32. From C to E is 8. From C to D is 24. From D to E is 13. And I think that does it. So these are all the weights. Your job, I would like you to find, let's say, use sorted edges. To find a good Hamilton circuit. I'm saying good because the sorted edge does not give you the best one. It just gives you one which is pretty good. A good Hamilton circuit starting and ending at, let's say, E. I will say again, don't think about this until the end, right? You just do your procedure. You don't care about where it starts and ends. Until you say what your final answer is, that's the only time when that becomes relevant. All right, see if you can do it. I hope you work this out. It's not so difficult if you understand the process. So let's write down my edges in order. The cheapest would be 8, and then I got 12 will be next, then 13. Like I said before, sometimes the hardest part is just making sure you get them all in the proper order. Then 15. Maybe I should do a little sort of check these off as I hit them to make sure I get them all. 13, then 15. Okay, then 19. Then 20. There. Then 21. Then what? I got 24, I think, is my next best. And then I got a 27 and a 32. All right. There we go. This is all of my edges in order, and we're just going to try to choose them in this order. So first I picked the 8, which is right there. Next I pick the 12, so I did the 8. Next I pick the 12, if it's allowed. It is allowed, it goes right here. How about the 13? The 13 is here. Actually, the 13 is not allowed because it makes 3 meet at the E, so I don't do the 13. The 15, here, also not allowed because it makes 3 meet at the E. The 19 is allowed. Doesn't make 3 meet anywhere, and it makes no smaller circuit. Okay. The 20, I believe the 20 is allowed. And now you can see we've chosen 4 edges. You can continue to go through the list if you want to, but actually the last edge must be the one which connects these 2 ends. I'm looking for 5 edges total because I have 5 points. So the last edge must be this one, the 27. And this is my Hamilton circuit. Just that nice little star pattern. I said find a Hamilton circuit starting and ending at E, so now is the only time this is relevant. I write my final answer as if it starts and ends at E. So I'm going to say E, and then, as always, there are 2 ways that you could go around this thing. Let's just write, and either would be correct. Let's just do this one that goes to B first. So E to B to D to A to C to E. There you go. The sorted edges procedure.